Okay, so here's an idea of what I think Project 3 is going to look like. And I do imagine Matter Day will go over at least maybe one or two tasks conceptually in class, depending on time constraints. All right, so we basically have to, we're basically dealing with high quality bandpass filters. So for the first task in this given circuit here, basically for the first task, which again I imagine Matter Day may or may not go over, we have to derive equations for R1, R2, and R3, like so. And for this, there's actually a separate attachment of for task 1 of how the equation actually works out. Well, first of all, I imagine for task 1 we have to transfer this function, rewrite this whole circuit into frequency domain circuit, just like how we've been doing generally since day 1, like so. So here's the separate attachment for task 1 of how to work this out using nodal analysis, KCL, like so. There are actually 9 equations altogether, so I'll let you, kind of pause this tape and kind of walk through it. And actually, I actually, obviously we have to handwrite our nodal analysis for the given equation on our own. Because obviously if we were to put this on our final report, that's a duplicate and that will give us a 0 for the report. Right? So we're solving for V naught over Vi. That's our transfer function, like so. So then afterwards, this is where we have to solve for R1 and R2 and R3 individually, like so, for the given bandpass gain, our bandwidth, our quality factor, our frequency, and so on. So for R1, our Q over K, we're given our numerical value for Q, numerical value for K, and so on. So this is for R1 and R3. Let's see, R2. Oh yeah, R2. Well, that's a tricky one. So again, kind of pause the tape, go through this slowly, and so on. In addition, not just for this task, but for all the tasks in this project, there's actually hints that Matter Day posted, like so. And here it is. These are the hints. Well, this is for after we solve our circuit using KCL for the first task, like so. And like I said, I think the Q is given. Is it not? Yep. Oh. What is it? Okay. Okay, I stand corrected. The numericals values for Q and K are actually on the next task. Okay, I stand corrected. My mistake. Task 2. But yeah, basically for R1 and R2 and R3, these are just symbolic values. So yeah. And you've already seen the attachment for the equation, the written nodal analysis for task 1. So yeah. All right. Then for task 2, use the results from task 1. Use these results to design a high Q bandpass filter with a center frequency of 700 Hertz, quality factor, that's Q, of 10, and a band gain of 5, that is K. We use capacitors 1 microfarads, so basically we have to create a schematic in LT Spice, and bow plot for the magnitude and phase of transfer function. No MATLAB included just yet. And here it is. Okay, so how did we get all this? Is from here. Except, okay, so for the bandwidth, the omega naught, I imagine that's 700 over 10. Okay, strike that, reverse it, forget I said anything. So the bandwidth, omega naught over q over 140 pi. Well, that should be straightforward, so I'm sure we'll be able to figure that out. Okay, so, okay, continuing with task 2. Now, in this case, you can see what happens with R1 and R2 and R3. That's because the original R1 and R2 and R3 are multiplied by the scalar factors. The scalar factors, so I'll go through this very slowly. K sub m is our scalar factor. So for instance, R1 multiplied by K sub m, the scalar factor, R2 also multiplied by K sub m, and so on. And basically for this given somatic, you just plug those values in to R1 and R2 and R3. And our AC analysis is given as well, and the expectation for that should give you this bulb plot right here. All right, so task 3, we have to write the transfer function h of s in terms of s equals j omega. Then we have to write the MATLAB script to plot the magnitude and phase angle, the bulb plots. Now, I'm still at work. I still have yet to think over with my MATLAB script. It's still pretty rough because my plot from the MATLAB script is still not yet meeting the expectations. So I plan to check in with Matterday on that. But anyways, so here we're given our transfer function like so. So how did we get this? Basically, you just follow this transfer function here from task 1. Where, in this case, the same values, where k is still at 5. The k is still the band gain of 5. Q is still the quality factor of 10. Now, the bandwidth, okay, so the bandwidth is 140 pi, so yeah, right here. Yeah. That's how you get this. And then it looks like, for this result, comes from the fact that, okay, so from this final result, you can see I'm circling here with this cursor here, probably comes from when this is multiplied by 2 pi. That's where I think it's coming from. I know I'm sounding a little vague in my explanation, but yeah. Okay, and then once you write your MATLAB script, expectation should look exactly like this, like so. And there you go. Okay, so then task 4, in which I will be responsible for presenting in class, we have to derive the amplitude coefficients of the Fourier series, the harmonics, pretty much just like what we were doing in Lab 6, if anyone has started that yet last Friday. I don't know how behind anyone is with Lab 5 and so on, but Lab 6 is pretty much similar to this, except, okay, so Fourier series, the harmonics are a train of rectangular pulses x of t, where the pulses are asymmetric with respect to the origin. And the width of each pulse is 0.125 seconds, and the period, t, capital T, is 0.5 seconds. And then we use equation 4.3, like so. Hang on a minute. Okay. Give me a second here. Okay, now here's another attachment Matterday also posted for task 4. The Fourier series coefficients calculations. So, so again, we use equation 4.3. And I think we should also take into consideration equation 4.2, where omega naught is 2 pi over t. And we're not even assuming it. I know we're going to take this as well. Equation 4.2. Right? So, and it's actually given to us. And it looks like, well, I don't want to be too positive on this matter, but if I think this is the case where, okay, the math is all worked out for us, well, clearly we need to handwrite the calculations ourselves. Okay, it's because because it looks like we're using obviously some calculus here, but we need to do this ourselves in our own handwriting, you know, and to include it. Because if you just copy this, obviously, on our final report, it's obviously going to be a 0. Enough said. So, let's see. So pretty much everything is well, I can't speak for you folks, but for me, well, some of the stuff is pretty much well explained. We all know how matter days notes can be in general. So, but this is what I think is going on. Okay, so omega naught is 2 pi over capital T, and so on. 2 capital T sub 1 is 1 over 8. 1 over 8 equals 0.125 seconds, as shown from the picture in the task 4 description. And then, of course, dividing that by, dividing this by 2. There you go. And then, of course, multiply T sub 1 by omega naught. There you go. All right. Okay, so symmetric pulses and our asymmetric pulses. The focus is obviously on the asymmetric pulses. And there you go. And then, again, it looks like the math has already worked out well for us. I recommend you trying this out independently. And if you're still struggling, well, guess what? I guess this will save you. I'm guessing this might save you. Right here. This whole thing worked out. But please do it in your own handwriting, like I said. Using equations 4.2 and 4.3. For 4.2, we substitute that into omega naught. So we use that to substitute 2 pi over capital T into omega naught. So yeah, I strongly recommend doing that. So you can copy this whole thing down, but again, omega naught, plug in 2 pi over capital T. Please, please, please. Okay? Just like what the note says here. And this is in order to prove the asymmetric pulses like so. All right. So after that, this is where now we design the high Q bandpass filter using LT Spice. It's pretty much similar to what we did in task 2. All the same values except for the frequency. Okay. So to do that, again, same as before, except for R1 and R2, R3, we use a different scalar factor, K sub m, like so. Right? Because, how do I say this? Okay, so we have our original R1, R2, and R3, like how we solved it in task 1. We got our bandwidth, but this is a different value now for the bandwidth. Okay, this is a different value for the bandwidth. Our K sub f is 4 pi, right? And then 1 over k mkf is our km, which of course is our scalar factor. So basically for R1, R2, and R3 individually, we multiply each resistor by this scalar factor. And that's how you come out with this. So now, okay. So now for this, I only performed one schematic thus far, but it looks like, based on the hints that I'm looking at here, we need to do more than just one. So, and it looks like for this schematic, it looks like for this part, we would have to use the same R results from task 2, I believe. Yeah, so it looks like in task 4, looks like we use these results from task 2 to get this bow plot. Let's see. So it looks like for the pulse function in the in a bunch of different schematics, we're performing different behaviors for the pulse function for the schematics. So yeah, it looks like we're doing more than one schematic for this one, to the best of my explanation for task 4 that I will be presenting in class Thursday. All right, so then tasks 5 and 6 involve a twin T-notch filter. So task 5, twin T-notch filter, has a high Q band reject filter. And a version of it is shown below, and a different version is shown in the 10th edition of the textbook, chapter 15. But I assume almost everyone has the 11th edition for this class. So, transfer function is band reject filter, band center frequency given by omega naught, 1 over 2 RC. And the 3 decibel notch, which is apparently, actually, I think this is pretty straightforward to calculate. The width of the 3 decibel notch is 2 minus 1 minus m. What is m? M is 0.9. So 2 times 1 minus 0.9, that should give you the 2 times 1 minus 0.9 times omega naught. And that omega naught is 314 radians per second. So 2 times 1 minus 0.9 times 314, and that should give you the final result of the 3 decibel notch width. So we use R as 59K, and you just plug that into the R's. So where you see 2R, you just plug the 59K ohm in and multiply that by 2. Like so. For the R, obviously just, well, you know what to do from there. And here. For the lowercase mr, you just multiply 0.9 times 59K. Pretty straightforward as far as setting up the schematic. And then you implement the circuit and show the both plots. And the expectation of this, and well, everything's given right here. This is the expectation. Looks like this is the expectation for the both plots in task 5. And it looks like we're doing more than one schematic at this point. So, let's see. I'm going to guess C1, C2, you're multiplying these by 2. Looks like you're multiplying. Are we multiplying by 2? I don't know. I'm babbling. Forget I said anything. Think on this. Alright, so the last test, task 6, design another twin T-notch filter with a different value for C. For C1, C2, and C3. Having a center and frequency of 2 Hz. Same as before. Design your new schematic for LT Spice. I recommend saving this and then save as a different file name for task 6. Whatever you want. Just to save yourself some time. So the expectation should be, in terms of the bow plot, should look something like this. You see the question I highlighted right there? Think on that, because obviously I still have yet to do as well. And in case you can't see the schematic up close, I'll zoom it in. Pretty much, I'd say we're copying off the hints that Matterday is given, but I would just be a little careful. I would just check in with Matterday to see if that's what we should use. But in my opinion, these hints seem to be pretty helpful. I still have yet to think on tasks 5 and 6, I'll be honest with you. So yeah. I hope my explanations were clear. Maybe some of them might be vague. I can understand. Project 3.